think we'll get started. I hope everyone had a good weekend. What I'm going to show you first is that I did post the first assignment. I that was just this morning, so let me show it to you and make a couple of comments here. All right, 304 is here. Okay, so there's the first assignment, and I'll open it in a second. I struggled with trying to figure out, like, should I write my own problems? Because I mean, everyone knows that all of the solutions to the Griffiths problems are online, and you can just simply go and look those solutions up. Um, but then I thought, so what Griffiths does, he has these starred problems, and the starred problems are supposed to be the important ones that everyone should try. And more than that, he will go use the results of the starred problems later in the book. So it's important that we do them. And so your assignment is basically the starred problems from the first chapter. Uh, I thought about, like, okay, even if I'm not going to write my own problems, maybe I could modify them in some way so that they're not just identical to the solutions. But then I said, well, if people really wanted to just get solutions, they'll just put those questions into ChatGPT and it'll happily give you the solutions step by step, as in as much detail as you want. So I thought, rather than burning all of my time doing that, what I'm going to do is assign Griffiths problems and encourage you not to use the solutions. But that's going to be up to you. You get out of this course how much effort you put into the course. So I recommend strongly that you do these problems without looking at the solutions, without asking AI to solve it for you. Now, I'm not saying that you shouldn't use AI for anything. I think it can be a very good tool for kind of refining and deepening your understanding of concepts from the course. But if you use it as a shortcut to solve problems for you, you're just hurting yourself. And so I'm going to leave it at that. I am going to grade those first four problems, and then here are some other recommended ones that I suggest you try, but I will not be grading them. Okay, and so the due date is September 24th. That's a week from Wednesday, this coming Wednesday. All right, good. Any questions about any of that? All right, so then what were we working on? We were working on this idea of stationary states. So what we did is we started with the time-dependent Schrodinger equation. And so there it is. It involves partial derivatives with respect to time and position. So our first step was to say, well, what if we had a potential that was constant in time? So it had no time dependence. And then we try and do a separation of variables for the wave function. So there'll be a psi part that depends on x and a phi part that depends on t. So if we do that, then we can go and, take the time derivatives is going to only act on the second factor. The spatial derivatives will only act on the first factor. We stick that into the time-dependent Schrodinger equation, and this is what we get. So here's the t derivative acting only on the function of t. The next step was to divide by psi times phi, and what that resulted in was this expression, star. And what's nice about star is that we have functions of time only on the left and only functions of position on the right. So we've kind of separated out the time and position dependence. And so what we argued last time was that, well, let's suppose that we're sitting at some position, x is fixed. And so at some time t1, the left-hand side and the right-hand side are equal to each other, but then we stay at x. we keep x fixed, so the right-hand side of the equation is not going to change, but we allow time to go to some other time t2, where the stuff has evolved in some way. Well, it must have evolved in a way so that this combination is constant because the stuff on the right didn't change. And so the left-hand side and the right-hand side have to be equal to the same constant. That constant we're going to show today is going to be the system energy. And so we're going to use E for that constant. Okay, and so I think that's essentially where we got to last time. And so we're going to try to work on this a little bit. We're going to start with the left-hand side of the equation. That is the time-dependent part, because that part is easy to deal with. What I'm going to do is I'm going to move the dt over to the right, and I'm going to divide by the IH bar. And so we could end up with, if we integrate both sides after doing that manipulation, we get d phi over phi is equal to, so let's see, let's multiply both sides by minus I. By multiply by minus I, we get minus I times I, which is +1. So we get +1 on this side and minus I over here. And then I'll divide by h bar. And we had our constant E, and we're going to multiply by dt, and we still have to integrate. E is a constant, so I'll take it outside of that integral. So this is going to be the ln of phi, and this is going to be minus I over h bar E times t. And if we exponentiate both sides, we'll end up with phi of t is equal to some integration constant c e to the minus I e t over h bar. This is an integration constant. Okay, so that's fine. We'll keep that in the back of our minds for now. One thing I like to do is I always like to check the units to see if they make sense. E was just our constant from our separation of variables. I already told you it's going to be an energy. So if it is energy, it's going to have units of joules times T is a joule second, and that has h bar has the same unit. So the argument of the exponential is unitless, which is good. All right, so that's one side. What about the other side? The other side is the position dependent part. And so I'm just going to copy it down. So it's minus h bar squared over 2m minus h bar squared over 2m. Actually, maybe I can get it on the page here. Okay, so the stuff above the blue has to be equal to E. So I'm just going to multiply through by psi. And so we'll get a d2 psi dx2. And then we have a plus v, but we have to multiply through by psi. Whoops, I got to be careful. And we're going to set that equal to E, but we have to multiply by psi. All right, let me just remind you that this is the lowercase Greek letter psi. So, and it's different than the uppercase one. Remember, we said the uppercase one was going to be a function of position and time. And so the lowercase one is just a position dependent variable. Okay. So there's not much we can do with this until we specify a form for the potential. This is called the time-independent Schrodinger equation. So we're going to have two versions of the Schrodinger equation. One has a time-dependent part, the IH bar d capital phi dt, and this time-independent part acts only on the position dependence of the wave function, and there's no time in it anywhere. Okay, so this expression is called the time independent Schrodinger equation. So for short, I might write that as time independent Schrodinger equation. And the first one that involves time would be the time dependent Schrodinger equation from now on. Okay, so a lot of our time and effort will be devoted to solving the time independent Schrodinger equation. For the time dependent part of the wave function, little psi of x. We can only do this once the v of x has been specified. And remember, this separation of variables that we have just done works only when we have a potential that doesn't depend on time. But that's going to be almost all the cases that we consider in physics 304. Okay, so the full time dependent wave function. Okay, so capital psi is going to be equal to lowercase psi times phi, our function of time. But phi is always going to have that form that we wrote down, e to the minus I e time, where is it? Minus e, here it is, minus I e times time over h bar. So we know its form. There is some constant out front, but usually the integration constant is absorbed into lowercase psi. And so if we do that, we could write that phi is e to the minus I e t over h bar. And then a full wave function that includes the time and position dependence would be written as lowercase psi e to the minus I e t over h bar. Okay, so I want to make some comments about these so-called stationary states. And in fact, we haven't really talked about why we're calling them stationary states. And so I want to justify that terminology now. All right. So states of this form are called stationary states. Since the probability distribution, so remember, the way we get probability distributions is we take the absolute square of the wave function. So let's see what happens when we do that. So we'll take the full wave function that has the position and time dependence. And so that's going to be little psi e to the minus I e t over h bar. And then we have to multiply it by its complex conjugate. Now, this little psi could be a complex function. In general, it will be. So we have to take the complex conjugate of the whole thing, the product of the spatial and time-dependent parts. And so what do we end up with? It is going to be nothing happens to this first factor. But then now we're going to apply this conjugate to both these factors. So there's going to be a psi star. And then this I is going to become a plus I in the exponential. And here's the nice result, that those exponentials that contain the time dependence are always going to cancel out when we calculate these probability densities from the absolute square of the wave function. And so that's an important feature that we want to keep in mind. And that's really why, that's one of the reasons why we're going to use the term stationary state. Because if you look at this, the full wave function and just the spatial part, their absolute squares are equal to one another. Okay, so we get the probability density from just the spatial part, and there's no time evolution. Okay, so the probability density, the full wave function squared, is equivalent to just the spatial part squared and is independent of time or stationary. Okay, I want to go a little bit further with this stationary state terminology. And so maybe we'll go here. And it's nice because it'll give us a chance to review our momentum operator, which we just developed last week. So recall the momentum operator. If you remember, the way that, or the result that we got, was that the momentum operator was essentially a spatial derivative. There's some factors up front. Those factors are minus I h bar, and then it's d by dx. All right. So if that's the case, let's think about the classical kinetic energy, 1/2 mv squared. Another way to write that is the momentum squared, mv all squared, divided by 2m. So the equivalent of the classical kinetic energy in quantum mechanics is acting with the momentum operator twice. So becomes, let's see, 1/2m, and then we'll have the momentum operator twice. So we'll get minus IH bar twice, and then 2 spatial derivatives. And then let's suppose that's acting on our wave function. I'm only going to put the spatial part because this is a spatial derivative. Okay, so the minus and the minus cancel, but then we get an I squared. And so I squared is -1. And then we have H bar squared. So we get minus H bar squared over 2m. And then we have 2 spatial derivatives acting on the spatial part of our wave function. But if you go back to our time independent Schrodinger equation, minus h bar squared over 2m, 2 derivatives of the spatial part of the wave function. This is exactly the first term in our time independent Schrodinger equation. And so that first term is the kinetic energy. And clearly, this is just the potential energy. We have it specified by our problem, multiplied by the wave function, E times. So this is kinetic energy plus potential energy is equal to mechanical energy. All of those terms multiplied by the spatial part of the wave function. Okay, good. So this is the first term in the time independent Schrodinger equation. and it corresponds to the kinetic energy. All right, so if we write down this time-independent Schrodinger equation again, it looks like this if I factor out psi. And then it has to be equal to E times psi. And this stuff in here is our energy-like operator, and it's called the Hamiltonian. If you've taken, or when you do take the advanced mechanics course, Physics 328, it's usually a term 2 course. You'll talk about Hamiltonian classical mechanics, and the Hamiltonian is defined as the sum of the kinetic and potential energy. And so that name comes from classical mechanics. So this is called the Hamiltonian. And because it's an operator, it's operating on our wave function. We'll put a little hat symbol on it. And it is the energy operator. Okay, so more on this stationary state terminology. What I want to do is I want to calculate an expectation value for the energy. And so we had this kind of prescription for calculating expectation values. So let's go through that procedure and let's remind ourselves of how we're going to do it. So let's calculate the expectation value for the energy. And so in general, if I wanted the expectation value of any operator, I'm going to do the expectation value of the Hamiltonian, but this could be position or momentum or any other dynamical variable that you can define an operator for. The way you calculate that was you take the integral over all space or over the domain of your problem where your wave function exists, and then you have the conjugate of the wave function, and then you have your operator, and then you have your wave function, and you integrate with respect to x. So I'll put in minus infinity to plus infinity in this case. All right. Now notice that I've used just the spatial part. Why didn't I put the time part in it? Or why don't I have to put the time part in it? Yeah.
Let's say cancel out like the
Yeah, just like they did for the probability density, right? For this factor, we'll have an e to the minus I e t over h bar. And then when we take the conjugate, the I goes to plus I. And those two exponential factors are just going to cancel. And they'll always cancel. Okay, yeah.
If an operator had a derivative with respect to time.
Yeah, you can't do that then. So yes, that is true. If you had an operator that has a time derivative, that's going to be a problem. Yeah. Or, I mean, so yeah, you could not have a time dependent operation in here and use just the spatial part.
Yeah.
Yeah. Yeah. Okay, good. So, well, this combination of the Hamiltonian operator acting on phi, well, the Hamiltonian is just the time-independent Schrodinger equation. And if we look at the time-independent Schrodinger equation, it just gives us E times the wave function back. So this is just E times phi. But now E is a constant, where E is a constant. We said E has to be a constant because it was our constant that was associated with our separation of variables. And so because it's a constant, we could take it outside the integral. So then we get E psi star times psi integrated overall space, but this is our probability density, and if our wave function is normalized, then this is just 1. And so therefore, the expectation value of our Hamiltonian is just the energy of that stationary state. Okay, good. So I want to push this a little bit further, and let's calculate the expectation value of h squared. So next, let's find expectation value of h squared. All right, so the procedure is the same. It doesn't matter that it's squared. The way we calculate doesn't change. We take the integral of the conjugate of the wave function, and then we put whatever operator we have. In this case, it's the Hamiltonian squared, so it's just 2 copies of the time-independent Schrodinger equation acting on psi. All right, so let's do this slowly. We'll separate our 2 copies of the Hamiltonian like so. And then we'll say, well, we've already dealt with this. This is just E times psi. E is a constant. We'll take it outside. So we get E integral psi star. We still have 1 copy of our Hamiltonian operator. So there it is. And we still have psi. Yes. So, but what is this? We just did this.
That's E.
Yeah, this is the definition of the expectation value of the Hamiltonian. But we just calculated that, and it is indeed E. And so this is equal to E. That's another constant. Well, in fact, it's just E times E. And so therefore, the expectation value of h squared is E squared. Okay. So the variance of the Hamiltonian is, so one of our other results was that the square of the standard deviation, or the variance, could be determined from the expectation value of some quantity squared minus the expectation value of that quantity then squared. We just worked out this is E squared and this is E, but then we have to square it, so we get 0 for the variance. And so this is E squared minus E squared, which is equal to 0. So our stationary states are states of definite energy. The standard deviation tells us the spread of a distribution. So remember, the way we're going to think about this is we prepare a bunch of states with identical environments, identical initial conditions, and then that's our ensemble. And then we let them all start evolving. And then at some time, we go and make a measurement of the energy. And we do that for every single copy in our ensemble. What this is telling us is we're going to get 0 spread. Every time we're going to measure E, 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 E. There is no variation. So our stationary states of the form so the full position and time dependent wave function as its position determined by, or its spatial dependence determined by little psi, and we need to be given a potential to work that out. But the time dependence will always be of this form. And these states have a definite energy given by E. So we'll write down what I tried to convey in words. That is, every member of the ensemble of states has the same energy with no variability. Okay, so what we'll end up doing in general is the following kind of sequence of steps. So when we solve the time independent Schrodinger equation, and I'll write it down again. So minus h bar squared over 2m. We can write the derivatives as ordinary derivatives, in fact, because psi is only a function of x. So what we'll find is that when we're given a potential, and we'll start actually doing that this week. When we're given some specified potential, we're going to find a family of solutions. So for a given potential, we will find a family of separable solutions. And so by separable, all I mean is that the total time-dependent wave function can be written as a product of a spatial part and a time-dependent part. And so each member of this family will have its own energy. So with each with its own fixed and constant energy. Okay. Now, what we're going to try to do then is, from the solutions for little psi, we can go back and reconstruct the general solution for the full time-dependent wave function. So the general solutions to the, let me try to emphasize, time. Now this is now dependent. The time-dependent Schrodinger equation. So I'll write it down. Just we'll have both versions of the Schrodinger equation right next to each other. Okay. So the general solutions to the time-dependent Schrodinger equation will be linear combinations of the separable solutions. Will be linear combinations of the separable solutions, which are of this form. Okay, so explicitly, in other words, the full time-dependent wave function will be constructed as so. There's going to be some coefficients, Cn, and then we'll have our spatial parts of our solutions. And then we're already going to know what the time-dependent part looks like. That's always going to be minus e to the minus I en t over h bar. What we don't know are these coefficients, so we're going to have to develop some procedure for finding those coefficients. The task will be to find the coefficients. Cn. This is a lot like if you think back to 232. What we did is we wrote down a Fourier series for periodic functions. And so we could expand a periodic function in terms of sines and cosines of different frequencies. But there was these coefficients in front of those terms, and we had to have a mechanism for finding those coefficients. And it's essentially like a Fourier decomposition. And we're going to have something very similar here. Yeah.
Does that mean that these linear combinations are also stationary states in the end, right? Like they're
I know they have time dependence right there.
Yeah, but sorry, the not stationary states, but like when you take their probability distribution, they still don't change in time.
We're gonna do an example. We'll see how that looks. Okay. So I think we're gonna do an example in just a minute that will answer that question. So let's wait a second. So it will be the case that assuming the separable solutions does not limit the class or type of wave functions we're considering. We can reconstruct the most general solutions to the full time-dependent Schrodinger equation from a superposition or a linear combination of separable solutions. Okay, so let's do that example that I think will try to address your question right now. So this example is from Griffiths, and it's the first example in chapter 2. So example 2.1. So here it is. Let's suppose a wave function is a superposition of just 2 stationary states. So it's the simplest possible superposition of states that we could think of. So what we're going to say is that the wave function at time t equals 0 is going to be equal to C1 times 1 stationary state, which is a function of x only, and then C2 times a second stationary state. So this is indicating this is t equals 0.
Which is why we removed the exponents.
Yep, but we're going to put it back in. So the first question is, let's find the wave function at some later time. Well, all we have to do is put those exponential factors in. All right, so let's see. It's going to be C1 psi1 of x e to the minus I e1 t over h bar. Remember, these two states are in general going to have different energies. And so the E that goes in the exponential is E1 for the first state, and it's going to be E2 for the second state. So we'll get a plus C2 by 2 e to the minus I e2 t over h bar. All right, and that's all there is to it for that first part of the question. B is find the probability density. And so I think this is the part that's going to address your question explicitly. So all we're going to do is take this and multiply it by its complex conjugate. And let's see what we get. So psi squared is going to be psi star times psi. Whoops. Okay. Now, in general, it's possible that these coefficients are complex quantities. So I'm going to treat them like complex quantities. When we take the conjugate, we'll get a C1 star, and then we'll get psi1 star, and e to the plus I e1 t over h bar, and then the same thing for the second term, C2 star, psi2 star, e to the plus I e2 t over h bar. And that all has to multiply just the original wave function, where now the exponentials are going to have these minus signs. But in fact, it is not going to be a complete cancellation of all the time dependence, because we're going to get cross terms that don't cancel. And so let's see how that works. All right, let's do the easy ones first. We'll do, there's 4 terms in this product. Let's do this term times this term. Okay, so we're going to get C1 squared. And psi1 times its conjugate is psi1 squared. And this time, these exponentials, they just annihilate one another. They cancel. And then we do the second term times the second term. And it's going to look exactly the same. We're just going to have 2s instead of 1s. Okay, but now it gets more complicated because we have cross terms. And let's see, we'll do this times this. So we get a C1 star, C2, psi1 star, psi2, E. Okay, we'll go minus I. And let's see, what do we get? If I put a minus I, we'll get an E2. But over here, we have a plus I, so we're going to have to write this as minus E1. And then T over H bar. Okay. And then we have one more cross term, these two. And so it has similar kind of form. What's it going to be? C1, C2 star, psi1, psi2 star, e to the, I'll do plus I this time. I'm going to do plus I, so that's going to be a plus E2 and a minus E1. So it's going to be E2 minus E1 T over H bar. All right. And so you can see that, in fact, the probability density is no longer time independent. Once we construct this superposition of stationary states, the probability density is no longer time independent. both these cross terms have a time dependence. To go a little bit further, let's make a simplifying assumption. This is what Griffiths does in his example, is he says, well, what if all of these coefficients and all of the wave functions happen to be real? So let's just see what happens. It might illustrate this case a little better. It will show us in a little more detail what that time dependence actually looks like. If C1, C2, Psi1, Psi2 are all real, then, okay. This probability density is going to be, well, if these are all real quantities, then the absolute square is the same as just the regular square. So it's going to be C1 squared, Psi1 squared, plus C2 squared, Psi2 squared, plus. All right. So now we're going to have C1, C2, Psi1, Psi2. If we just ignore the conjugates because everything's real. And then we're going to get C1, C2, Psi1, Psi2 in both these cross terms. So we'll have C1, C2, Psi1, Psi2. In fact, I guess I don't need this bracket. Plus. And then it's going to multiply. In fact, I think I'm going to move this, give myself a little more space. All right. So what's it going to multiply? It's going to be e to the minus e2 minus e1 over times t over h bar. And then it's going to be an e to the plus I e2 minus e1 t over h bar. Okay, so it's e to the I e2 minus e1 t over h bar plus the same thing, but with a negative sign in the exponential. So if I have a product of complex exponentials like this, what does this simplify to? E to the ix plus e to the minus ix.
The third expression that's cosine of.
That's cosine. It's
Sorry,
two
cosine
times
two.
cosine. So this is 2 cos e2 minus e1 t over h bar. Let me just remind you where it comes from. So this is a bit of an aside. One of the greatest equations in math is Euler's equation. So e to the plus minus I don't know, x is equal to cos x plus minus I sine of x. Okay, so if I was to take e to the plus ix plus e to the minus ix, in fact, let me just do plus minus. Let's do them both at once. We would get cos x plus minus I sine x. Sorry, we're going to have to do, I'm going to do the plus one first. So I take the plus sign. And then I would do plus or minus. And now I'm going to take the minus sign here. So cos x minus I sine x. So if I was to use the plus sign, I'd get cos plus cos is 2x, 2 cos x. If I was to, and then we'd have I sine x minus I sine x, and they would just cancel. So if I was to take the plus sign, so this is the plus sign, we'll get 2 cos x. And if I was to take the minus sign, I'd get cos minus cos is 0. I'd get I sine x minus I sine x, so it's 2I sine x. Okay, so therefore, cos x is e to the ix plus e to the minus ix over 2. and sine x is equal to e to the ix minus e to the minus ix over 2 times I. These are so useful and so common that that's worth committing to memory, because it's very convenient to be able to jump between complex exponentials and trig functions. Okay, so anyways, we were calculating this probability density, and what we're left with is, after this aside, we get the square of the full time-dependent wave function, which is a superposition of two stationary states, is c1 squared psi 1 squared plus c2 squared psi 2 squared plus 2 c1 c2 psi 1 psi 2 cos of e2 minus e1 t over h bar. Okay, so this wave function has an oscillatory term, and the frequency of those oscillations depends on the difference in energy between those two states. Okay, so I guess that's what we'll write down. So here, the reconstructed time-dependent wave function has a probability density that oscillates with a frequency, an angular frequency omega, right? If we set what's in here to be omega t, then omega is the difference in energies divided by h bar. E2 minus E1 over h bar. So the more separated those two energies are, the higher the oscillation frequency. All right. So what I want to do next is I want to calculate the expectation value of the energy. We just did this for stationary states, and we saw that we got constants. The expectation value of the energy for a stationary state is just E, the constant from that separation of variables solution. So what happens with this reconstructed full time-dependent wave function? So we're going to find the expectation value of E. All right. So the expectation value is the integral of psi times our operator. So this would be psi star times psi dx. Okay. So there'll be a bit of writing here, but that's okay. Our wave function is this linear combination of two stationary states. So there's nothing we can do much with that, but then we'll write down our Hamiltonian operator. That's really just the time-dependent Schrodinger equation. That's going to act on the original wave function without the conjugates. Like so. All right. And so we'll just do this slowly, write it out step by step. I'm not going to do anything to this first bracket. I'll just copy it down. But what I'm going to do is I'm going to take our Hamiltonian operator and I'm just going to distribute it into the second bracket. So we'll have a C1, and then we have H hat acting on psi 1. In fact, maybe I'll be even more explicit. Let's do it like this. And then we'll do plus C2. And then we'll have our Hamiltonian operating on the second stationary state. And then we have our dx. So the beautiful thing about this is that we already know that stationary states have definite energies. So this is just E1 psi 1, and this one is likewise E2 psi 2. Okay. So what do we get then? So let's see. Let's do let's just multiply this out. Again, let's do the nice terms first. We'll do this first term times the first term. So we're going to get C1 squared, psi 1 squared, and then there's a factor of E1 hanging out. So we get, well, in fact, maybe we can do this like so. C1 squared E1, and then we have the integral of psi 1 squared dx. And then let's do second term times second term. C2 squared is a constant, it's going to come out the integral. E2 is a constant, it's going to come out the integral. Psi 2 star times psi 2 is going to be absolute square, that's going to be inside the integral. So it's C2 squared E2 psi 2 squared dx plus. All right. Now we have cross terms. And just like we had cross terms before. So we'll do this one times this one, I guess. We'll start with C1 star, C2. We pick up a factor of E2. And then we have the integral psi 1 star, psi 2 dx. And then we have a similar cross term that involves E1. Psi 2 star, psi 1 dx. All right. Now this looks like a mess. We can simplify this quite a bit. What is this integral going to be?
One.
1. Yep, exactly. Remember, psi 1 with only the spatial dependence is still a normalized wave function, and so it gives the probability density for that stationary state, and the probability of finding that particle anywhere in space, minus infinity to plus infinity, is 1. Same thing here. All right. Now we haven't talked about it, but I'll just preview. So there's no way that I would expect you to know this right now, but it will turn out that these integrals involving mixtures of stationary states are going to be 0. They're going to be called orthogonal. It's like taking the dot product between two vectors. When you take two vectors that are perpendicular to one another and take their dot product, you get 0. So we will eventually show that these are going to be orthogonal states and that these integrals will go to 0. So in just a bit down, let's say in the near future, we will show that if psi 1 and psi 2 are two solutions to the time independent Schrodinger equation with E1 not equal to E2, then these integrals phi 1 star, phi 2 dx is going to be equal to phi 2 star, phi 1 dx. It's equal to 0. And so we'll say that these two stationary states are orthogonal to one another. we will say, whoops, that the stationary states psi1 and psi2, two solutions to the same time-independent Schrodinger equation, are orthogonal. The terminology gets even more weird if the functions are orthogonal and normalized. They're called orthonormal. But anyways, more on this later. If we accept that that is going to be true, then the result for the expectation value of the energy is C1 squared E1 plus C2 squared E2. Whoops. So the expectation value for the energy is like this weighted sum of the energies of the stationary states, and the weights are determined by these coefficients that we have to find in order to reconstruct the full time-dependent wave function. So getting back to your question, the probability density is not a constant in time. However, the expectation value for the energy is. Okay, so this is energy conservation in quantum mechanics. All right, good. How are we doing time-wise? We got 15 minutes. All right, so we're going to solve our first problem. It's one that you have seen before in Physics 200, I am sure. It is the infinite square well. So let me make some general comments about it, and then we'll dig into it. After we do the infinite square well, we'll do some other examples in chapter 2. In particular, the one that's probably the most important will be the harmonic oscillator, and that's one that you haven't done. Okay, infinite square well. So the first example of a quantum system that we'll investigate is the infinite square well. Okay, so to find, in general, for any problem that we're going to be given, to find the psi x from the time independent Schrodinger equation, from time independent Schrodinger equation, we need to specify the potential. And so for the infinite square well, the potential is going to be infinity or 0. It's going to be 0 if it's between some specified coordinates. I'm going to use minus a/2 to a/2. This is not what Griffiths used, and it's going to be infinity otherwise. Another way to say otherwise is that the absolute value of x is bigger than a/2. So I'm not doing the same boundaries as Griffiths for a couple of reasons. One is Griffiths provides a solution. I'm sure you've all read it already before coming to this class. So you can see the details of the Griffiths solution in his book. You've also seen it in Physics 200. I want to show you that if we shift the potential in space, we'll get the same sets of solutions, even if the math is a little different along the way. Okay, Griffiths uses the range x goes from 0 to a. So our well is going to be the same width. I've just translated it in space, and translating a well in space shouldn't affect the solutions. And we'll find out whether or not it does. All right, so here is a sketch of the potential. Here's x. And so I'm going to put a by 2 is maybe 1, 2, 3, something like this. This potential goes off to infinity. 1, 2, 3, something like here's minus a by 2. This also goes to infinity. Here's minus a by 2. Here's plus a by 2. Here's x equals 0. And let me just say that the potential is infinity all through this space. I made it asymmetric.
Yeah.
Okay, the easiest way for me to fix that is to move the center line. Okay, so right about here, something like that. Okay, good. So, before we actually go solve this problem, like there's the potential for this to give an impression that this is just like some artificial textbook problem that has no relevance to actual physical systems. And so I just want to give you some examples of where at least a physical system could approximate a infinite square well. So examples of physical systems that approximate. So I'm not saying that they're exactly the same, but approximate infinite square wells. Okay, so one is electrons in a thin conductor. So if you imagine like a little strip of copper, maybe it's like copper tape, so it's very thin. It could be extended in the x and y directions, but we can make the thickness in the z direction very thin. And the electrons in this conductor are confined to be inside the conductor. They don't just easily fly out. And so we're restricting our electrons in the z direction to be in some narrow space. And so that approximates this kind of potential here. So electrons are confined in all three directions by strong electrostatic potential. So if you like, that would be like a three-dimensional infinite well. But if we make, like I said, the x and z directions large, then we could really kind of focus in on the z dependence. Okay, another example is cold atoms in an optical trap. Sometimes also called optical lattice. So this is a relatively modern kind of experiment, like in the last, I don't know, couple of decades or something like this. So if you've heard of Bose-Einstein condensation, you can collect a bunch of atoms. You start by trapping them in some kind of magnetic trap. And what you do is you lower the height of the trap. Then the most energetic of those atoms, the ones that have the most kinetic energy, fall out. And you're left with only the atoms that have lower energy. And so you lower the average energy of this collection of atoms. And you keep doing that until they get very, very cold. And then they can form this so-called Bose-Einstein condensation. Then what you could do is you could hit these atoms with lasers in all 6 directions, like the sides of a cube, that laser imparts momentum on these atoms and confines them spatially. The light is periodic, and so you end up getting this oscillation in this confined space, which is like the well. I have a picture of this. So I'm going to try to show you the picture if I can find it. Where are we? Here we go. All right, cold atoms. So this is supposed to represent our Bose-Einstein condensate, a collection of cold atoms. These are the lasers that are confining them to some region, and they effectively make these little, this blue thing is like a potential well, and then you can put individual atoms in these wells and you can study them. And they're confined in the X and Y directions, and that's like something that approximates an infinite square well. So what I'll do is I'll put these pictures in our notes, but I'm going to do that offline a little later after class. So I'll leave some space for those pictures, and let's add a page. Good. All right. And the last one I'll talk about is neutrons in a nucleus or a nuclear potential. Now, I don't know a lot about it, but apparently the potential is flat inside the nucleus and rises sharply at the surface. And so that sharp, rapid rise is like our potential. It's flat, 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 and boom, goes up. Okay, and so there's 3 sort of examples where this actually might approximate real physical systems. So not only is it a convenient problem for us to think about, it's also one that has some relevance in real physics. All right, so we only have a few minutes left, but let's write down the time-independent Schrodinger equation. So it's minus h bar squared over 2m, 2 derivatives of the spatial part of the wave function, plus v times phi is equal to e phi. All right, so outside the well, so when the absolute value of x is bigger than a by 2, since v goes to infinity, we require psi equal to 0 in order for the time-independent Schrodinger equation to be satisfied. So what am I saying here? If I let v go to infinity, I can't let my quantum system have infinite energy. And so the only possibility is I put in 0 here to kind of cancel that infinity. But if I put 0 here and here and here, then we just get 0 equals 0. So the wave function cannot exist outside the well. Okay, and so this is really just a trivial solution, and it's the only solution. There's no wave function outside the well. One way to think about it, and maybe this will be the last thing that I write down, is if you want to have like a classical analog, what you could imagine is like some kind of steep hill. Something like this. Okay, my hill is not going out to infinity, but I can make the height of the hill h very large. And if I say this is where we're going to put y equals 0, then if I put a ball in here and release it from rest at this point, then it has maximum potential energy and it'll start rolling down, and as it rolls, it'll pick up speed. And as it gets further and further down the slopes, it'll start going faster and faster. At the bottom, it has its maximum speed, maximum kinetic energy, and then that process just reverses, and we end up just doing this constant exchange between kinetic and potential energy. But the ball never has enough energy to escape the well. And of course, if we have an infinite well, it doesn't matter how much energy we give our particle, it can never get outside. All right, and so these are our classical turning points, which occur when there's zero kinetic energy and all potential energy. All right, so next time we'll think about what happens inside the well. All we're going to do is we're going to write down Schrodinger's equation inside our well. E is equal to 0, and we're going to try to solve this second order differential equation. And again, I'm going to use a process that differs from Griffiths. So your assignment is to study the Griffiths solution, and then come on Wednesday prepared to see a second version of the solution, hopefully giving consistent results. All right, thanks very much, everyone. Have a good couple of days.
When you do the linear combination of stationary states to the new one,
Yeah.
will you always end up getting the